Here we will see how linear systems can be interpreted in terms of matrix algebra. Let's again look at the typical system of linear equations in variables x. There will be n of those, and we'll have m equations. But already interpreted is in the language of vectors. The vector of the left side which itself is a linear combination of columns matching the right hand side. There's not much to it, but then we called this the product of a matrix the bulk in the extended matrix of the system with the column of unknowns. So that was the definition of this product, which gave rise to everything else. And that is just A times the column X of unknowns, and we are equating it with B. Alternatively, we could look at this as a function of X, and A will be the matrix of this linear function, and we are solving this function equation. So this language is very convenient for seeing all the features of systems of linear equations. For example, what we looked at before is a homogeneous case where the right hand side is 0, and that would be solving the system of this shape. The column of unknowns times some matrix is equal to 0. The solution set of this is always non-empty because we have just 0 solution always for us there, and it is of big importance in all the aspects of linear algebra and has its name. It's called the null space of matrix A. And analogously, we could look at the same thing in terms of linear maps. So we'll be solving this equation, linear map of the matrix F, of matrix A on X is equal to 0. So the set of those in terms of maps is called the kernel, but it's just the same thing. The different names signify the importance of it. An easy statement which we had about solutions of homogeneous systems that they are closed under addition and scaling, and that is in notations. Say for the null space, that is like that. If we have two solutions of homogeneous system, their sum will be a solution. And now using matrix arithmetic is easy to see, because what we are to check is that this product of matrix A and the sum of two columns is 0, but we can rewrite it as a sum of products, and each of them is 0 as a vector, so that will be the 0 vector. And the second property we had is that scaling, again, of any solution will give us a solution. Even easier, if we multiply scaled solution with a matrix, we can rewrite it as the product of the matrix and the solution scaled. And since it's solution, we have 0. And the next statement we had is about non-homogeneous systems or in homogeneous systems. So if we're solving this equation and we happen to have two solutions, then the difference will be a solution of a homogeneous system. And it's easy to see again using this matrix arithmetic, because what we'll have here is the difference of the products. And since x and y both solutions, these two products are the same right hand side b. So we're subtracting the vector from itself. We are ending with a zero vector. So y minus x is a solution of the homogeneous system, is a vector in the null space. And turned around, it would just say that any solution can be written as one particular solution plus something in the null space. So again, for example, uniqueness of solutions is only possible when the null space of the matrix is 0. That is the same as to say that there are no free variables. All the variables are determined, are pivots. And that is it. See you later.